Hi, I'm Shauradip Majumdar. I'm a PhD student at EPFL in Switzerland, and in this video, along with my colleagues, we are going to take you through a journey of PrISMa. PrISMa stands for Process Informed Design of Tailor-Made Sorbent Materials for Energy Efficient Carbon Capture. At PrISMa, we aim to develop a technology platform to tailor-make cost-efficient carbon capture solutions for a range of different CO2 sources and CO2 sinks. To achieve this goal, PrISMa unites the efforts of world-leading research teams from Heriot-Watt University in the UK, EPFL in Switzerland, Centre for Energy Research in Norway, and Berkeley Lab in the US. Now, when we think of capturing CO2 and decarbonizing our planet, there can be different CO2 sources, as you see in this illustration, like coal power plants, natural gas fields, to even directly capturing CO2 from air. And once we have separated our CO2 from these sources, there can also be different possible sinks where the CO2 can go, like geological storage, chemical products, or enhanced oil recovery. And this sourcing combination then helps us determine the process requirements for a particular separation. With this goal in mind, we have organized our work in 4 different work packages. And now, through a combination of slides, live presentations, and laboratory demonstrations, we'll give you an overview of each of these 4 different work packages.
The aim of Work Package 1 is to establish a methodology based on the effective carbon price metric that allows translation of specific carbon abatement requirements into key performance indicators of carbon processes for screening and synthesis of novel materials. Starting point has been noticing that the absorption technology has been widely studied with 2 distinct domains. On one side, material science, on the other, process engineering. But we noted also the formation of a gap between those two. PrISMa aims to fill this gap by developing a platform that, based on case studies, would further develop screening models which are fit for purpose model of absorption processes, which allow to look for synergies between material and process and identify a set of promising adsorbent materials. This information would then be passed to other work packages that will deal with the synthesis, characterization, and testing of those top performing materials. And some data will then get back to Work Package 1 and used in full physical models for performances and benchmarking analysis. The expected outcomes is the ranking of existing adsorbents based on the effective carbon price in order to identify promising candidates. And further, the definition of target ranges of key parameters or target ranges of material properties to identify those adsorbent materials that leads to the best key performance indicators.
Now that we have the list of KPIs to evaluate from Work Package 1, we would screen our list of potential candidates for a given separation that is defined by a source and a sink. To do that, we need to compute a set of physical properties and adsorption isotherms. We used advanced computational techniques from molecular simulations and quantum mechanics to compute these properties. However, it's a significant challenge to link the world of properties to that of process modeling, and for that we use numerical techniques. This workflow allows to screen material databases to identify the top performing material.
When you think about a class of materials like MOFs, there are many of these structures available. I have a few examples here, but in principle, the number of structures are infinite. Like, you can change this metal, you can change the linker, you can add functional groups and enumerate almost infinite number of structures. Clearly, we cannot screen all these materials in our databases for our application. Therefore, what we try to do is to use methods from machine learning to make sure that we have a representative set of structures that not only cover all possible type of structures, but at the same time avoiding screening many similar structures.
By bridging this gap between molecular simulations and process simulations, we can thus identify the most promising materials for carbon capture out of millions of possibilities. And once we identify these materials, we now head over to our experimental teams in work packages 3 and 4, where we study more about these materials in details.
Work Package 3 involves material synthesis and characterization with EPFL, Berkeley, and Harriet Watt involved. The package aims to synthesize and characterize promising material that have been identified in Work Package 2. For MOFs at EPFL, we have synthesized a set of reference MOFs using solver thermal synthesis, a spray drying technique, and our robotic platform. We will continue to use the robotic platform to develop and optimize synthetic conditions for the novel MOFs that Work Package 2 concludes targets for the particular carbon capture application.
In Professor Jeff Reimer's lab at LBNL, we specialize in using NMR to characterize the molecular level interaction between carbon dioxide and the absorbent material in order to help elucidate absorption mechanisms in mixed metal oxides and MOFs. We have developed a gas dosing system for NMR that can simulate flue gas by incorporating high temperatures and various humidity levels in our dosing setup. After the sample is sealed, it is placed inside the NMR probe, where we can measure a variety of NMR active nuclei in the absorbent and adsorbate, such as carbon-13, to look at the formation of carbonate and bicarbonate upon CO2 absorption.
The very first characterization technique that we use after the synthesis of the MOF is X-ray diffraction. By using X-ray diffraction, we can compare the predicted pattern with the experimental one, and we can make sure about the structure. After the characterization, the next step is the absorption measurements, and for that, we use a gravimetric analyzer. By using the gravimetric analyzer, we can measure different gas isotherms such as nitrogen and carbon dioxide. Before doing the absorption measurements, we activate the sample to make sure that all the solvent molecules are removed from the pores and the pores are available for the gas molecules. We can perform the absorption measurements at different temperature ranges.
As part of the Work Package 3, we at Harriet University synthesized layered double hydroxide-based CO2 sorbents using various synthesis methods. The synthesized samples will be characterized using diffraction, microscopic, and spectroscopic techniques. The promising materials will be evaluated for industrial carbon capture applications.
As responsible of Work Package 4 here at Heriot-Watt University, we have created a universal protocol to allow us to screen any adsorbent material in the process identified in Work Package 1. At the same time, we have designed and built a dynamic Rigg-Love scale that we will use following the product developed to test and screen the material synthesized and characterized in the Work Package 3.
With this, we come to the end of our video. I hope that we have been able to give you an overview of our work in PrISMa. I take this opportunity to thank our sponsors and industrial partners. The environmental clocks are ticking and we are already running late. So let's hurry up and capture this CO2 before it captures us. Thank you.